All right, hello everyone, and welcome to the Math 2414 Week 3 review. In this one, we'll mostly be covering some trig substitution, which I know is everyone's favorite, and also we'll be getting into some partial fractions. All right, so we're going to be starting out with some trig substitution. Now, it seems kind of daunting at first, but really it's not all that bad. So let's kind of relate trig substitution to something you're already a little more familiar with, U substitution. So in U substitution, what we do is we try and make a substitution to make things a little easier on ourselves. Am I recording?
Yeah.
I am. Okay, perfect. So in U substitution, we try and make a substitution where we say U is some more complicated function of X. And what this does is it lets us take a more complicated integral and rewrite it in a simpler form. And importantly, what we're doing is we're not changing our integral at all, we're just making it look a lot nicer for ourselves. Well, trig substitution, we kind of have the same end goal in mind. We want to make a substitution that allows us to rewrite our problem in a way that's just simpler for us to solve. And the way we usually do this is using our trig identities. So let's just start out with an example. If I had the integral of the square root of 4 minus x squared. Well, my whole goal is to use a trigonometric identity to simplify this. And what I know is I know that 1 minus sine squared of theta is equal to cosine squared of theta. And my goal is I want to make a substitution because I have something of the form a constant minus a variable. And if I can make a substitution like that, I can put in something squared, and then the square root of something squared would just give me the thing originally. So that's kind of my end goal. So I'm going to say I want my x squared to be equal to 4 sine squared of theta. Because what that lets me do is I can replace my x squared with 4 sine squared of theta. So now I have the integral of 4 minus 4 sine squared theta. Well, importantly, this gets me x is equal to 2 sine of theta if I take the square root of each side. So my dx is now equal to 2 cosine of theta d theta. And that's the substitution I make. So now let's go through this and simplify as much as we can. I'm first going to pull my 4 out of my square root. So because it's a 4 in every term, I factor out a 4 first, and then I pull it out of my square root. And what do you know? We end up with that 1 minus sine squared that we wanted at the beginning. And that, coincidentally, is also how I decided to choose that my x squared should be 4 sine squared of theta. This term right here, this 4 right here, should basically always match the coefficient on your constant. And we still have times 2 cosine theta d theta. Now, continuing onward, I have 2 times 2 is 4. I'm going to write that out front as a coefficient. The square root of 1 minus sine squared, well, I know 1 minus sine squared is cosine squared. The square root of cosine squared is cosine, and then cosine times cosine is cosine squared theta. And now I just have to integrate cosine squared theta. Well, to integrate cosine squared theta, we talked about this last time. We need to use some of our trig power reduction identities. In this case, we need to get our cosine squared into a lower power. And the identity we're looking for here is cosine squared theta is equal to 1 plus cosine 2 theta all over 2. So now this integral becomes 4 times the integral of 1 plus cosine 2 theta all over 2. I can pull out my 2 as a coefficient, so I have 4 divided by 2 is 2. integral of 1 plus cosine 2 theta. And now I can just integrate. Here I have theta is the integral of 1. The integral of cosine 2 theta is 1 half sine 2 theta. And of course I have my plus c. Now of course I'm not done because my original problem was in terms of x, so I need to write my problem in terms of x. Luckily I know that x is exactly equal to 2 sine of theta. So I can get what theta is equal to. Since I know that x is 2 sine theta, I know that arc sine of x over 2 should be equal to theta. And to get that, I just divided both sides of this equation here by 2, and then took the inverse sine. So now I can plug that in for theta. I'm also distributing my 2 as we go along. So 2 theta is 2 times arc sine of x over 2 plus, and in this case, I don't ever want to leave arc sines inside of trig functions. So in this case, I'm actually going to replace my sine 2 theta with 2 sine theta cosine theta. So 2 times 1/2 cancels. And now I can actually go ahead and plug in my theta. Sine of arc sine is just whatever's on the inside. So sine of arc sine of x over 2 is just x over 2. And now I have the cosine of arc sine of x over 2. And there is a nice way we can solve for this. And if we use a geometric interpretation, it kind of makes a little more sense. So let's start with that. If I think about arc sine, we can think about arc sine as taking in some kind of triangle and giving out an angle. And I know that sine, by using SOHCAHTOA, is opposite over hypotenuse. So in this case, my opposite side is x. My hypotenuse is 2. And then just using Pythagorean theorem, I see that my third side should be the square root of 4, which is 2 squared minus x squared. And one thing to notice, this is a kind of way you can really quickly check you did your trig substitution right, is this 4 minus x squared shows up right in your problem back here. That's just a brief side note. Anyway, if we wanted to take the cosine of this triangle generated by our arc sine, cosine is equal to adjacent over hypotenuse. And the adjacent side here is the square root of 4 minus x squared. And the hypotenuse is 2. So that's our cosine. And all that's left is to just finish simplifying a little bit. We're going to combine our 2's. And we're done. Let's see, I believe. Any questions on that? Oh, one thing I did forget to do is I forgot to distribute my 2 here as well. So this should be a 2 sine theta cosine theta. Remember, this 1/2 is being canceled by our 2 right there when we make our substitution. So this should actually be x times 2 there. So then 2 times x over 4 is x over 2 instead. Just a slight mistake on my end. Any questions? All right, let's do a quick recap then. So we start out with 4 minus x squared. And our whole goal is to make a substitution so that we can use this identity 1 minus sine squared is equal to cosine squared. And to do that, we first said I need to match my constant coefficients. So I need to make x squared equal to 4 sine squared theta. From there, I can factor my 4 out, and then I have 1 minus sine squared theta on the inside, which I can substitute out for cosine squared theta. Of course, when I do that, I also need to change my dx into a d theta. So I did that using the same substitution, simply taking the derivative of it. Then I had my complete substitution. I kept writing it in simpler and simpler terms until I could integrate it. Once I integrated it, I undid the substitution using my handy dandy triangle and some geometry, and then I was done. All right. Time for, I think, some general rules. So in general, there are 3 substitutions we can make. If we have the form the square root of a squared minus x squared, well, then the substitution we might want to make is probably going to be x is equal to a sine theta, or x squared is equal to a squared sine squared theta. I usually like to do this one first, because then it's really clear what my a squared should be. But that's the substitution we make when we see something in this form. And then the identity we'll use is going to be 1 minus sine squared theta is equal to cosine squared theta. If you see something of the form instead a squared plus x squared, and of course we might end up having constant coefficients right here. We can just factor those out first. But if we have something of the form a squared plus x squared, we can make the substitution x equals a times the tangent of theta. Or again, x squared is equal to a squared tangent squared theta if we just square it all. And then the identity we'll use is 1 plus tangent squared theta is equal to secant squared theta. And finally, if instead we have x squared minus a squared, well, we're going to want to make the substitution x equals a secant theta, or x squared is equal to a squared secant squared theta. And the identity is simply what happens if we subtract 1 from each side of this identity. So these are the 3 forms you might see for trig substitution problems, and then the 3 different identities you'll want to use, as well as the different substitutions. All right, so time for some practice problems. All right, I'll give you a good chunk of time to work through these. All right, let's go over these. So for the first one, it's the same kind of form. We have a squared minus x squared, so we're going to kind of make the substitution. X squared is equal to 4 sine squared theta. And of course, this means that x is equal to 2 sine theta, which means, again, theta is equal to arc sine of x over 2. This also means that dx is equal to 2 cosine theta theta. So now we're ready to go ahead and make our substitution. Our x becomes 2 sine theta. Our square root 4 minus x squared becomes square root 4 minus 4 sine squared theta. And we have multiplied by our dx, which is 2 cosine theta. Okay, now 4 minus 4 sine squared theta, we can pull out a 4. The square root of that becomes 2. And then that'll cancel with the 2 on top. And here we have the square root of 1 minus sine squared theta is the square root of cosine squared theta times 2 cosine theta, which is equivalent to, now here we have sine theta divided by the square root of cosine squared theta is simply cosine theta, and that'll cancel with the cosine theta there. So we're left with the integral of 2 sine theta d theta. The integral of 2 sine theta is naturally negative 2 cosine theta plus c. And this would be equivalent to negative 2 times the cosine of the arc sine of x over 2. But of course, we never want to leave it in this form, so let's go ahead and draw out our triangle. We know that theta is equivalent to the arc sine of x over 2. So in this case, our sine gives us that x is our opposite, 2 is our hypotenuse, which means that we have the square root of 4 minus x squared. Again, this matches the square root we have here in our original equation. So we can take the cosine of this triangle, which is the adjacent side, divided by the hypotenuse. The cosine would give us 4 minus x squared. That's a terrible looking x. 4 minus x squared, square root of that, of course, all over 2 plus c, which gives us negative square root 4 minus x squared plus c. Is that what you got?
I think so.
Cool, cool.
Looks like it.
Nice, nice. I guess one important thing to note is we could technically also be making the equivalent substitution 1 minus cosine squared theta is equal to sine squared theta. That's the same trig identity, so if you wanted to instead make your x squared equal to 4 cosine squared theta, you could do that as well. All right, let's look at the second one. The second one, we have 1 plus 9x squared. Now that most closely matches the second shape here. So we're trying to make the substitution 1 plus tangent squared theta is equal to secant squared theta. So if we want 1 plus 9x squared to become 1 plus tangent squared theta, well then what that means is this 9x squared should be equal to tangent squared theta. So this is the substitution I'm going to use. We take the square root of both sides, we get 3x is equal to tangent theta, or x is equal to tangent theta over 3. So dx is equal to 1/3 secant squared theta d theta. Additionally, I know that theta is equal to the inverse tangent of 3x. So let's go ahead and make our substitutions. We know that our x should become a tangent theta over 3. We have now the square root of 1 plus our 9x squared becomes tangent squared. And our dx becomes 1/3 secant squared theta. All right. So let's go ahead and see what cancels. We have a 1/3, a 1/3. I'm going to pull that out front as a 1/9. We also have tangent of theta. 1 plus tangent squared, that'll go to the integral of secant squared theta times secant squared theta. the square root of secant squared is just secant, so we have 1/9 times the integral of, I'm going to write it this way, secant squared theta times secant theta tangent theta. So here's my secant squared, it went right here, my tangent went right here, and then my secant squared turned into secant theta. Okay. Well, now I can actually set this up just like a U substitution problem. So then I have secant squared turns into U squared. I have secant theta tangent theta. That turns into my du. Well, now I need to know what the secant of theta is. So I'm going to push this right up here. And theta is the inverse tangent of 3x. So again, I'm going to draw my triangle. I know that tangent is opposite over adjacent. So here I have 3x as my opposite, and I can think of it as just being divided by 1. So then my hypotenuse would be the square root of 1 squared is 1 plus 3x squared is 9x squared. And again, you'll notice this 1 plus 9x squared matches what I have in my integral. So then the secant of this, secant is equal to hypotenuse over adjacent. So the hypotenuse is square root 1 plus 9x squared, the adjacent is 1. So I have square root 1 plus 9x squared cubed. Any questions on that?
One thing I'm kind of confused about, so why do you write your arctangent inside of the secant? Is that just a way to tell yourself that you need to do the triangle?
Yeah, so basically I'm just trying to take it step by step. So I write my arctangent inside of my secant because I originally made this substitution up here, right? And then that substitution, if I rearrange it, I get what theta is equal to. So when I solve and I get 1/27 times secant cubed of theta, what I need to do is I need to make sure that I'm substituting that theta out again for exactly what theta is equal to. So that theta there just gets plugged in there. And then I write it just to make it very clear.
But mathematically, it really doesn't affect anything.
Mathematically, it doesn't really affect anything. If you kind of skip writing it in there, it's fine. It's just that this statement is what happens when we substitute it right in, and then next I simplify. So if you're simplifying and substituting in one step, that's fine, as long as it's clear what you're doing. No other questions?
Okay.
Perfect. All right. Let's actually go ahead and move on to partial fractions then.
We haven't actually started that in class.
You haven't started that in class. You're just doing trig substitution, huh?
That's for us. I know there's some other professors who read that.
I kind of want to throw in some partial fractions just because they're fun.
Okay.
So
That's fine.
we'll go ahead and do a few partial fractions.
I don't want getting head started with class.
Perfect. All righty. Partial fractions. Partial fractions are not that bad because you've been working with fractions your whole life, right? Or I guess not your whole life, but for several years now. So the whole idea behind partial fractions is if I asked you to add two fractions, let's say we had a fraction 2 over x plus 3, and then another fraction 3 over x minus 1. I could ask you to add those, right? And how would you go about adding them? Well, you need a common denominator first, right? And the easiest way to find a common denominator is to just multiply all the denominators together. So I'm going to say this is equal to 2. And in order to get an x plus 1 on the bottom, or an x minus 1 on the bottom, I need to multiply by x minus 1 on top. Right? So then I can have plus 3 here. Again, I've already got my x minus 1, so I need to multiply by x plus 3. And then that would get me 2x minus 2 plus 3x plus 3 all over my new common denominator. And that would get me 5x plus 1 all over x plus 3 times x minus 1. Right? So that's just a quick review on how we add some fractions when they have some functions in them. But we can actually undo this process. So instead of starting on this end and moving over to my 5x plus 1 answer, what if I started with this and I wanted to get back to this? Well, that's what we call partial fraction decomposition. And it's really helpful because these two things separately are a lot easier to integrate than this thing together. Because we can do both of these integrals with really simple u substitutions and get integrals of natural log. This is a little harder. So let's just start out with an example. I like starting with examples. Let's say we had 4 divided by x squared minus 1. Well, what I notice is I can factor the denominator. That's equivalent to 4 times x plus 1 or x minus 1. There, I factor the denominator. Well, what I'm going to say is I'm going to say this should be equal to some number a over x plus 1 plus some number b over x minus 1. So now I'm just going to kind of add these two fractions together. And to add them together, again, I need to find the common denominator. So my a needs to be multiplied by an x minus 1. My b needs to be multiplied by an x plus 1. And on the bottom, I have x plus 1 times x minus 1. And that should be equal to 4 over x plus 1 times x minus 1. Which means that the numerators should match, since the denominators match. Which means now I have a nice equation right here. And importantly, this equation should hold true for every single value of x, because I'm saying that these two things are exactly the same. They are the same thing, just rewritten in different forms. So for x equals to positive 1, I have a times 1 minus 1 is 0, plus b times 1 plus 1 is 2 should equal to 4, or 2b should equal to 4, which means b should be equal to 2. If instead I say x is equal to negative 1, well, now I have a times negative 2 plus b times 0 is equal to 4. So negative 2a is equal to 4, so a is equal to negative 2. Now all of a sudden I can write out that my original 4 over x squared minus 1 is equal to negative 2 over x plus 1 plus 2 over x minus 1. Which means I can rewrite my integral as the integral of negative 2 over x plus 1 plus 2 over x minus 1 dx. And both of these integrals are pretty easy to do. The first is negative 2 times the natural log of x plus 1. And the second is 2 times the natural log of x minus 1. And we're done. Did that make sense?
Okay.
All right. Hit me with some questions. Which part did you get a little lost on?
Like, get the first initial set, and then it's just new to me, so that's probably why it's like.
Yeah. So let's just walk through the process. First off, we kind of want to factor the denominator, because when we factor the denominator, that tells us what fraction parts we're going to have. In this case, we factored it into an x plus 1 and an x minus 1.
So how do you do that when it gets more complicated?
When it gets more complicated?
Is that when I should know my like a squared plus 2ab plus b squared?
Right. So you're going to need to know how to factor in order to be able to factor the denominator. Sometimes they might give you a denominator that's already factored, which is already nice, which is always nice. Sometimes you might just have to work with more complicated terms, and we'll talk about that if we get to it, but maybe next week. So we factor our denominator. That's our first step. Our second step is always going to be writing what our output should look like. So in this case, I said I'm going to have an x plus 1 fraction and an x minus 1 fraction. Because when I add those two things together, that's how I get my denominator of x plus 1 times x minus 1.
And of course, you put it like in a diagonal way.
Right, you can cross multiply to add. When you get a little more accustomed to doing partial fractions, a lot of the times this step is skipped and you might just jump straight to here. But basically, the idea behind it is we're just adding some two fractions, and we're looking for these two fractions, the numerators of those. So this is the big equation we're writing. These two things should be equivalent, which means because their denominators are the same, the numerator should be the same as well. So we pull off the numerator, and we say, well, these two fractions, or this statement should hold regardless of the value of x, because all I'm doing is I'm taking the two fractions and just adding them together. So it shouldn't change regardless of what value of x I put in there. Which means if I put in some nice values of x, that'll make some of my terms cancel. It's really easy to find my other ones. So the first one I said, I notice if I put in 1 for x, then the a times x minus 1 is just going to go to 0. So I put in 1, and I got 0 a's plus 2 b's is 4, so 2b is 4, and that let me find what my b value should be.
So that's like system of equations.
Yeah, it's just a system of equations, except you can pick whichever x values you plug in. Okay. So that's kind of how you get your new equations. You just put in a different value of x. And that's how I also found a. I said my next x value, I'm going to plug in -1, because again, that's going to be a nice, easy one that's going to get rid of any b terms. But I could have chosen 0, and then I would have gotten a times -1 plus b times +1 is equal to 4. So -a plus b is equal to 4. But since I already know b, so that's another way I could find it, if I so desired. But like I said, it's usually easier if you plug in things that'll just go to 0. So then that's how we found our a and our b. And then we just wrote it out according to the rule we made up here. So all I did is I took my a value, which was -2, and replaced the a up here. And similarly, I took my b value, which was +2, and replaced my b up there. Now, because this is exactly equal to my original integrand, I just replaced it in my integral statement. And then these are pretty simple integrals. We can do u substitution if we wanted. Say like letting u equal to x plus 1, then du is just equal to dx. So then the integral of -2, we can pull the -2 out front as a coefficient. 1 over u du, and 1 over u du is of course natural log of u. Like that. And that's where our first integral comes from. Similarly, we can do the same thing for our second one, and we have our plus c as well. Make more sense now?
It does. I'm still a little lost on the systems of equations part. I'll probably figure it out when I try to do it on my own.
All right, practice problem it is.
also, when I should start thinking about partial fraction decomposition is when I see a polynomial on the bottom that seems like it has can be factored, I guess.
Right. You want to think about it when you see polynomials in the denominator, especially if you think you can factor them.
And if we can't, then we should still try with negative b plus or minus mess.
Yeah, if you want. You might also want to consider looking at if you might know like U substitution. U substitution might work, especially if you have polynomials on the numerator as well. You might also want to consider some of your special trig integrals. So like if it's in the form x squared plus a squared, that might be a trig subproblem.
So you're saying we can have partial fraction decomposition and trig sub in the same problem?
Usually you don't see them in the same problem.
Okay.
I'm saying usually you might have to make a decision whether it's going to be one or the other. I'll give you some time to work through this. Good luck.
Thank you. Well, we also have like 13 minutes left.
Yeah. Yep. Should be good.
It's not possible.
To factor?
Yeah, because when I put it into the equation, I get a negative on the inside of the square root. Unless I missed
B
it.
squared minus 4ac. No, you shouldn't.
Because it's just,
You're reading it as x squared plus 4x minus 5, right?
yeah.
Okay.
Oh, that's where. we get fractions for anything? Okay.
Yes, A and B should be fractions.
Think they have probably no right, but usually,
All right. Should we go over it then?
yeah.
All right. So first off, we always need to factor our denominator. What did you get for the denominator?
I got x minus 4 and x plus
X minus 4 and x plus 4?
4. Yeah. Or is it x minus 2 and x plus 2?
I got x plus 5 and x minus 1.
Okay. Great start.
One way we can always check is we can just multiply them right back out together. So we have x times x gets us our x squared. X minus times negative 1 gets minus x. X times 5 gets 5x. And then 5 times negative 1 gets minus 5. That's x squared minus x plus 5x is plus 4x minus 5. How did you factor?
I used the negative b plus or minus square root of b squared.
Okay.
And so I just don't know what to do with that, I guess, is where I messed up. Let's see. I did this, and I just ended up getting 4, and I thought that would mean, like, that's what I plug in.
So you got negative 2 plus or minus 30 square root of 36, which is 6, right?
Yeah.
So you have negative 2 plus or minus all over 2a, right?
Well, it's simplified, because
Okay.
2 times a is,
So negative 2 plus or minus 3 then, right?
yeah.
Um,
Oh, wait, no, 6, because it was 36. Square root of 36 is 6.
but then we also need to divide that by 2 if we're simplifying that way.
Okay, well, I made all sorts of. Closing.
Oh, good. All right, we'll go over it. If you wanted to use the quadratic formula, you would get negative 4 plus or minus the square root of 4 squared is 16. And then 4ac gets us plus 20 all over 2a, so 2, which is negative 4 plus or minus the square root of 36 is 6 over 2, which is negative 2 plus or minus 3. Now this would get us a root of x equals to negative 2 plus 3 is 1, or negative 2 minus 3 is negative 5. And we can turn that into our roots by saying x minus negative 5, so x plus 5, and also x minus 1. That's how we can use the quadratic formula to get our roots as well. Does that make sense?
Yeah.
So it's basically you just take these solutions and write them in the form x minus whatever it is. All right. So we've got our roots, which means we can write a over x plus 5 plus b over x minus 1 should equal to 7 over x plus 5 times x minus 1. Now cross multiplying, we get a times x minus 1 plus b times x plus 5 all over the same thing, which means that 7 should equal a times x minus 1 plus b times x plus 5. Now, if x is equal to 1, I pick x equals 1 to cancel my a. I have that 7 is equal to 0a plus 6b. So b is equal to 7 over 6. Now, if x is instead equal to negative 5 to cancel my b's, I have that 7 is equal to negative 6a. So a is equal to negative 7 over 6. And again, I can rewrite my integral now in the form a, which is negative 7 over 6, x plus 5, plus my b, 7 over 6, over x minus 1, dx. And again, these are fairly simple integrals. We can just use our generic natural log, pull out our -7/6 as a coefficient. Similarly, pull out our +7/6 as a coefficient. Any questions on that? Nope. All right. Well, I think that's probably a good place to call it now. I don't want to get too far ahead of your class, so we'll stop there. Thank you for stopping in.